Hello everybody. In this presentation I will talk about dynamics and conformational transitions of GLIC investigated with computational methods. I think all scientists like to give presentations, but one of the disadvantage of presentations, a small group of people listen to your presentation and then everything is lost. So I didn't want this to happen, and I decided to record it and to put it onto YouTube, so that maybe some other people may find it beneficial for themselves. So let's start. Pentameric ligand-gated ion channels are an important class of proteins playing a role in signal transmission. We know that they play a role in channelopathies, and additionally we know that they play a role in anesthesia and addiction. And additionally, they are allosteric proteins, and these allosteric interactions cause them to change conformations between functional states. And of course, unfortunately, we don't know the mechanism of these conformational changes. And they exist in both eukaryotic and prokaryotic cells. But here I will talk about a prokaryotic example. Okay. Now, outline of my talk, basically I will introduce the architecture of the protein that I will talk about, which is GLIC. It's a prokaryotic pentameric ligand-gated ion channel. And my talk will be in two parts. The first part, molecular dynamic simulations of it, and the second part, it's a mechanoelastic modeling of it, basically. And today I will try to complete just the first part. Okay, let's just show the general architecture. I want to select laser pointer. Okay, here we are. Basically, it's a cylindrical shape, and the height of this cylinder is about 110 angstrom, and the diameter of the cylinder is about 50 angstrom. We have an orthosteric binding site between two chains, two subunits basically, and we have, as the name also implies, we have 5 subunits. And from the top view you can also see that this part is the channel part of it. Okay, now we have basically two domains in GLIC. Top part is called extracellular domain, and mostly it is beta sheets. It can be considered as a kind of skewed beta sandwich in each chain. I will come to details of individual chains later. And the transmembrane domain part is typically made up of 4 helices, and of course for some cases there are some intracellular domain also, but for the example that I will talk about, we don't have intracellular domain. So now let's talk about some details of the a single subunit. Basically, as I said, the bottom part is let's say the narrowest part. It's the pore part, basically selective pore part. Let's say we have 4 helices, M1, M2, M3, and M4, and the top part we have many beta strands, but we have some loops that are functionally very important. One of them is loop C, and the other loops that are functionally important are the loops between ECD and TMD. For example, pro-cis loop is one of them, M2, M3 loop, and loop F are some other examples, some other important functional loops. Luckily, we have 3 conformations of GLIC. One of them is closed state, as shown with red color here and in the structure also. Its resolution is 4.35 angstrom. We have locally closed state, and its resolution is 3.20 angstrom, and we have open state for HFI. Its resolution is the best, but as you also notice that they are quite similar, but the major difference is here, basically in TMD part. There is a tilt and a twist of M2 helix, which is lining the pore. So now you can see here much more clearly if you select just two subunits here. As you can see here, in locally closed and closed states, top part of M2 is in particular is very different. As you may also have noticed, resolution of closed state is quite low compared to the others, of course. And we refined this structure. I will talk. Okay, now before that, okay, when we superimpose their channel radiuses, you can see that open state is blue, obviously the largest channel radius. Locally closed state looks like closed state in the TMD level, but looks like open state in ECD level. And actually the average radius is one of the best way to see the differences between locally closed state, open state, and closed states. Okay, as you may have noticed, the lowest resolution is the closed state, and we refined it to 3.95 angstrom, and we wanted to see if these refinements can help us to see different dynamics. So basically we performed molecular dynamics simulations, and the essential idea is to solve Newton's equation of motion for millions or sometimes billions of times to get evolution of a system. When I say a system, my system is made up of protein plus POPC membrane plus water plus sodium and chloride ions, as you can see on the right hand side from the side view and from the top view. We performed 45 nanoseconds of constrained equilibration, and it was actually three-stage equilibration. First, we kept all heavy atoms of protein constrained, and then just backbone atoms, and then just C alpha atoms. And finally, we performed 15 nanoseconds of free equilibration without any constraint. And after that, we performed 1 microsecond production runs, and our production run conditions were similar to free equilibration. So, and it was MPD simulations. When I say MPD, we have about 150,000 atoms, and we have 1 bar pressure, and we have 300 Kelvin, and the simulated pH is 7. We have 4 states, and for each state we have a replica simulation. Now I would like to show you a general parameter which is used to assess the stability of proteins. As you can see, I am showing here on the left column stability of the proteins with RMSD in closed, locally closed, refined, locally closed, and open state. So now we can see, first of all, we can see the open state is relatively stable compared to the others. And additionally, we can see that the refined structure have some fluctuations in one simulation in particular, and similarly, the locally closed state also show a conformational change at this stage, approximately after half of the simulation, after 400 nanoseconds. But the question is, which part of the protein this conformational change occur? So for that, we plot RMSD for just ECD, and as you can see, yes, the closed, locally closed, and refined structures are similar. We wanted to plot RMSD across ECD and TMD also. RMSD in TMD is quite small actually, it's about 1 angstrom. 1 angstrom does not mean that there's nothing happening there, but it means just basically the conformational change is quite small. Now, if we plot ECD RMSDs here, you can see that the major conformational change is due to the changes in the ECD for locally closed, closed, and refined structures. But in open state, it is quite stable. Another parameter widely used to assess stability is RMSF, and we plotted RMSF for each case, closed, refined structure, locally closed, and open state, and we superimposed them in one graph. Now, we can see that the locally closed state, the blue lines or light blue lines actually, have slightly higher RMSF, but except some rare peaks, magenta peak here and green peak here, except some rare peaks, they are not significantly different from each other. As I said, the best way to characterize an ion channel is to measure its pore radius. Now, on the top line, you see overall radius, and in the bottom row, you see radius across just TMD region, which is actually the most important part for us because it is the narrowest part. Black line indicates average across the simulation. Dark gray shade is average of it, and light gray shade that you see here is basically maximal and minimal of these values. Here I especially put a line here. This is called 9' location approximately on the structure. It corresponds to this region, and it is typically the narrowest part. In general, what can we say about the average pores? The structures remain in terms of average pore radius, remain in their state. If it is closed, it remains closed. If it is open, it remains open. If it is locally closed also, it remains in the locally closed state, even though we can see some fluctuations. And here it shows us a better picture, actually, let's say larger picture, a better picture, but the narrowest part always remain as it is. So it's less than 2 angstrom. We decided to use some other parameters except pore radius to see, okay, pore radius is not changing, but what if the change is happening in just individual chains? To see that, we use two parameters. One of them is ECD twist, and the other one is M2 M1 distance. What is ECD twist? Okay, we define 4 center of masses. First, center of mass of entire TMD here with magenta sphere. Center of mass of entire ECD shown in orange sphere, and center of mass of ECD of an subunit, and again center of mass of TMD of the same subunit, let's say subunit A. Okay, now when you define 4 points, you can define a dihedral angle, and that's exactly what we did. ECD twist is a dihedral angle between when you look down, it is this region. So it indicates that if an individual chain twists or not. This is a parameter that you can use to characterize the changes in ECD. But what about TMD? For TMD, we have M2 M1 minus distance. When I say minus, it means basically the previous one. Previous in the sense of clockwise direction. Okay, so this is M2, then this is M1 minus distance, and we are basically measuring the distance based on their center of masses. Yeah. Now we plotted these values for the closed state, refined state, locally closed state, and open states. And here you can see the 2 simulation sets. First simulation set is the first row, and the second simulation set is the second row. Now, what can we see? First of all, we see that the open state is quite stable. It doesn't go toward locally closed state. It doesn't go toward closed or refined structure. On the other hand, locally closed state is quite flexible, especially in ECD in terms of ECD twists. You can see that it can go, but there is an important point here. All chains do not move toward closed, and only some individual subunits can move. Interestingly, in the second simulation set, you can see that even it can move toward the open state also. I mean that the M2 M1 minus distance also is changing, but again, only in some individual chains. Closed states and refined closed states are showing quite similar dynamics, and again you can see a transition between locally closed and closed states here also, here also. But a general conclusion about these parameters is locally closed states sample a wider region, and open state is the most stable states. As I said in one of the introductory slides on the structure, there are two parameters of M2 helix that one can use to characterize or to differentiate basically open and closed states. One of them is tilt angle and the other one is twist angle. Unfortunately, in our simulations, tilt angle was not showing any significant difference, but twist angle is showing us something. When we plot twist angle, as you can see, open state is obviously different from the others. The values are low. In particular, you can see the legends here, chain A, B, C, D, E are colored and average of them is in black line. And you can see that the black line in open state in both of the simulations are lower than the closed states, multiple closed states. So this is the first important, let's say, conclusion basically. What about the locally closed state? You can see that locally closed state in the first simulation we don't see a significant change, but in the refined structure we can see that some chains, twist angle of some M2 helices, I think it's in chain D and chain D and chain C. You can see that it approaches to the open state, but again the change is in particular subunit, not in all. And here also you can see a reduction and stabilization. And actually in the second simulation of the closed state also we can see a reduction in individual chains, again chain C and chain D. Okay, now two chains in the closed refined structure approach to the open, like, so we can consider basically this as a kind of, let's say, advantage of a refinement, but it is not a very clear, to be honest, difference, because in the second closed simulation set also we can see some changes. Okay, I want to talk about linear mutual information, just a general introduction. So basically we are looking for an answer to the following question: can we find dynamically correlated residues domains, and can we quantify the strength of these correlations? LMI is a parameter that can help us to answer these questions. It's very similar to dynamical cross correlations, which are widely used, but dynamical cross correlations change between -1 to 1, but here basically LMI varies between 0 and 1. 0 means low correlation, and in the color maps it is blue, and 1 means high correlation and it's shown in red. So I will show you here for the first simulation set, first row, LMI maps, and for the second simulation set. One particularly important important result of LMI maps, as you can see, locally closed states are more, let's say, have more brighter colors, and of course more red colors also. So linear mutual information is higher in locally closed state. The second one, even though it is not very clearly distinguishable, open state is the lowest. So probably high LMI in the local closed state, we can interpret it as sampling a wider basin and potentially a metastable state. Now, before finishing this part, I would like to connect my results to network theory. So what is a network? A social network is a relation between a group of people. So in a social network, each person is a node, and we can find edges or build edges between them. For example, if they are friends, we can put a line here, and we can define a weight for this friendship, let's say. And if they are friends, our edge value is 1. If they are not, it is 0, basically. Now the question is this: who is the most influential person in this network? We have two conditions. The first condition is he or she should have many friends, and he or she should have friends who have many friends. It is not sufficient to have many friends in a social network, whether it's online or real life. If the person have many friends who have many friends, it means that person is influential. So in terms of network theory, it means that the person should have high eigenvector centrality. What if I convert these persons to amino acids? Alice to alanine, Pierre to or any other amino acid. Okay, each node in this case is a residue or amino acid, and each edge is an LMI value that I have just shown you. Okay, in this way I can build a network, and then I can calculate the influential residues with eigenvector centrality. Okay, when we do that, interestingly, no matter which conformational state it is in, we find some influential residues that are almost at the same locations in all chains. And again, this is important, I think, because the conformational state does not change the importance or influential residues, and it is more or less in the same place in different chains also. So what are these chains? I projected these values, eigenvector centrality values, onto the protein. They are on M2, and we know that there are some ligands binding to this site, but still this is something in progress, whether it is related to the ligand binding or just some other properties, for example sensitivity to mutations. We are still searching on it, but we know that there are currently some studies connecting the network eigenvector centrality to allosteric pathways. So we think that the eigenvector centrality or influential residues in GLIC and in some in other proteins also may be related to their functional role. But the interesting thing for us in particular, despite the differences in linear mutual information, it was to see almost identical locations are described, identified. So I will finish this section with the conclusions. As you can see, all of the simulated states are stable across the simulations. Open state samples a smaller space. We can observe some transient conformational transitions, some local conformational transitions, for example, between locally closed and closed states. Another important result was high LMI values of locally closed state, and we identified dynamically influential residues, and these were typically on the residues on M2. And another important conclusion from molecular dynamic simulations was the time scale is too short. So we cannot observe full conformational transitions. And that's the reason of the second part of this talk, which I will explain, because the time scale is typically on hundreds of microseconds to milliseconds, and we are here just simulating a few microseconds in the best case. So we need some other methods to see the dynamics, to see something else, the allosteric interactions, how allosteric interactions are occurring. I will finish this part today. Have a good day, and hopefully tomorrow I will talk about the mechanoelastic modeling of the GLIC.